This section is entitled Comparing Variation in Two Samples. What are the requirements for this section? This is big. You need to always verify the requirements. Lots of times in the exercises that I work out, I forget to do that. In the last few problems, I didn't state that the ends were all bigger than 30. Okay, just because I'm being a slightly sloppy or a lot sloppy doesn't mean that you should be. Requirements are that the two populations are independent of each other. Are independent. That means they can't be paired up. And the two populations are normally distributed. The first population is normally distributed, and the second one is. And in this case, we have some silly notation that we have to be careful with. S1 squared, we can even just say S1. S1 is the larger of the two sample standard deviation. S1 is the larger of the two sample standard deviations. So sigma 1 is the variant, is their standard deviation is the population standard deviation associated, which is associated with the larger sample standard deviation. Anytime you see a subscript of 1, it's the information about the sample that had the larger standard deviation. It might be that S1 is bigger than S2, but you know what? The standard deviation of the first population is smaller than the standard deviation of the second population. It might be that N1 is smaller than N2. What N1 will be the sample size of the sample that had the larger standard deviation. The one with the larger standard deviation, they get the subscript 1. Okay? If that must be true. But it might be that sigma 1 is smaller than sigma 2, or it's bigger than sigma 2, or it's equal. It might be that N1 is smaller than N2, or N1 is bigger than N2, or they're equal. You get a subscript 1 if the standard deviation of that sample was the larger of the two. We have two samples, we'll get two sample standard deviations. And the one with the larger value will get subscript 1. If they're equal, then toss a coin as to which one you want to call 1. Okay, so any subscript of 1, it came from the population that had the larger standard deviation. Anything that has subscript 1 came from the population with the larger standard deviation. Anything, so based on what you have there by notation, Anything else that has a subscript of 1 came from the population that had the largest standard deviation. Did I say that enough times? The test statistic is the F distribution. And it is S1 squared over S2 squared, where the DF happens to be n minus 1. Okay. Now, we want to use a 0.05 significant level to test the claim. To test their claim that Diet Coke, and Diet Pepsi have weights with different standard deviations. Have weights with different standard deviations. Weights with different standard deviations. So, all right. So, if you had the sample weights of some Diet Cokes and you have sample weights of Diet Pepsis, you can't pair them up. You can't pair them up. So condition 1 has been met. The weights of soda cans, the weights of 12-ounce soda cans, they're going to be normally distributed. They're going to be normally distributed. Sometimes you have to assume that that's true. Okay, you do enough statistics in real life, not from a textbook or not from being in class. You learn what type of things are normally distributed and not normally distributed. Weights of cans are going to be normally distributed. Okay, and here's the information. Here's the information. Here is the test statistics. When it comes to Diet Cokes versus Diet Pepsis, Diet Coke has a sample of, say, 36, and the sample mean is 0.784794, and the standard deviation is, or of course, these units are in pounds, or some units of weight, because we're talking about the weights. And the standard deviation is 0.004391 pounds. And when it comes to Diet Pepsi, N is also 36. Their average sample weight is 0.783858 pounds, with the standard deviation being 0.004362 pounds. And they want us to use a 5% significant level to test their claim. All right? So we use the test statistic and we use the F table. if you use the test statistic, reading it from right below where I'm writing, S1. So now it's the largest standard deviation, that's 1. 0, 0 are the same, 0, 0 is the same, the next digit is 4, the next digits are 3, then you have 9 and 6. That's S1. It's larger. Let me say that again. 0.004391, 0.004362. These digits are the same, so it's a tie. Two numbers so far are equal. The next two are the same, they're equal. The next two digits are the same, equal. They're equal again. Here's the tiebreaker. Since the 9 is bigger, that top number is bigger. That's the S1. The larger one is S1. I said that a million times. So F is going to be 0.004391 squared divided by 0.004362 squared. If you remember your algebra, since we're squaring both numbers, if you want to save a little time and energy, you can do the division first. You can do the division first and then square it. And then you can square it. Either way, you are going to get 1.0133. That is the test statistic. Okay, that's the score that we got. Now we need to find the cutoff values. That is, we need to use the F table. Okay. And before we go there, we have our two-tailed test that and we have 5% for the tails, so 0.025 for the left tail, 0.025 for the right tail. Now we need to go to the F table. The F table just talks about the sample sizes. Now the F table, they don't have a lot of numbers on this table. They skip an awful lot. Be nice if I can find it. We're getting close. Okay. So, see where we're going to put this. Basically, you would love for the top to be 36 and the side to be, oh, you don't see up there. Gotta put the marker down first. Okay. Basically, you want the top heading to be 36, and you want the side heading to be 36, and you want to read that number right there in the middle. The only problem is that the heading goes from, the top heading goes from 30 to 40, it bypasses 36, and the left also goes from 30 to 40. On the left column, there's no 36. It goes from 30 to 40. Okay. So, the two numbers I like to look at will be 30-30 and 40-40. 30-30, 40-40. The number by 30-30. Now the top heading, actually I made a slight mistake. The degree of freedom is n-1. I really wanted 35 on the top and 35 on the left column. Now, the degree of the freedom for the numerator for n1 is 35. And in the left column is the degree of freedom for or the second sample, which is also 35. But again, there's no 35. So we'll go to 30, 30. And if I read this right, it's 2.0739. 2.0739. That's 30, 30. That's below 35, 35. Now we'll go above. We'll go to 40, 40. Top heading should be 40. Left heading should be 40. The number in between is 1.8752. 1.8752. So all I can guarantee you is that our exact score is somewhere in between 1.8752 and 2.0739. How fortunate for us, because F was 1.0133, the test statistics. It turns out that 1.8 is to the right of 1.0133 and also 2.07. All numbers in between these two are to the right of 1.013. This is where we accept, and in here we reject. Okay, so the claim is that the two sodas have weights with different standard deviations. And okay, so let's write up, see what we can get rid of. We can get rid of this here. So now we're talking about, this section is entitled Comparing the Variances. But now the square root of the variance is the standard deviation. So we could talk about this section also being called Comparing Standard Deviations in two samples. Right. So we have HO and we have H1. So we're talking about the standard deviations. I know immediately to put equal for HO. Now what about H1? The claim is that the two sodas have weights with different standard deviations. The claim is that S1 is not S2. Well, that doesn't have equal. So that's also S1. It's not equal. Right. Okay, so now I think I could erase everything except maybe the picture. And we can answer the question. Do we accept or reject HO? Well, HO says that they're different. But we're in the reject region. So we reject HO. Now, the claim and H1 are the same. So we're going to get the same answer for that. Since we're rejecting HO, that means we're not saying that they're the same. In here, we're saying that, I meant to say equal. In the middle here, we're saying that S1 equals S2. But we're rejecting that claim. So there is sufficient evidence to support the claim and H1 that the standard deviations are different. There is enough evidence to show that they're different. let's try one more problem. Let's go back to the vending machines. Weights of quarters. So, you know, again, weights of quarters, they're going to be normally distributed. Weights of quarters are used by vending machines to detect counterfeit coins. Prior to 64, before 1964, they used silver quarters. That is, when quarters are manufactured, they use silver quarters. And after 1964, so don't ask me what happens during 64, they stopped producing silver quarters. In fact, I did know they used to make silver quarters. I had tons of them growing up, but I don't know what they use now. But it doesn't matter. They use something else. Now, the statistics from some study shows the following. Pre-64, N happened to be 40. Their weights of these coins were 6.19267 grams, with their standard deviation of 0.08700 grams. Now let me save the line. Post 64, N was still 40, but the mean weight was 5.63930 with a standard deviation of 0.06194 grams. Actually, of course, 0.00. Now, we are to use a 0.05 significant level to test the claim. So here's the claim that the two populations of quarters have the same standard deviations. To test the claim that the two populations of quarters have the same standard deviations. Now, if they do, then you don't need to change your equipment. No, but you didn't have, their vending machine companies didn't need to change their equipment. Okay? Because if after 64, so now they have machines that have a tolerance. Okay? They have a little leeway on that weight. And if you are a lot more than that weight, if you weren't within a small range of that weight, they rejected your coin. Now, if after they stopped making the silver quarters, the variation got bigger, the standard deviation got bigger, well then the machines will start rejecting the coins. Okay. On the other hand, if the new coins have a smaller standard deviation, and if you look at it, they do. They have a significantly smaller standard deviation, well then that's good for the vending companies because they could modify their equipment to have an even smaller range. In other words, if you can guarantee that every quarter in the world is Q for quarter, the weights of quarters, we're in between this amount. Tens, 100,000, 10, 100, 100,000. These two numbers are within 100,000ths of a gram. If you can guarantee that, well, then it's going to be really hard for you to find a slug to put into one of these machines because there's very little variation in the weights. But now, if you said that it can be between 0.0000001 gram and 11 grams, that's a really huge range, and almost, when you can put a penny in, it'll weigh the right amount. You can almost put anything in and it'll weigh the right amount. So if their standard deviation of the coins got less, well then the companies could tighten up their equipment, make modification of their equipment, and then it'd be harder to use a slug, a fake coin. All right, well, we know that the test statistic is the larger standard deviation squared divided by the smallest standard deviation squared, which is the same as the division squared. The larger standard deviation is, I suspect that that's a typo. Yeah, that's a typo on the bottom one. It's 0.06. Nonetheless, the top number, this number, is larger than that number. So that's what goes on top. 0.08700 divided by 0.06194. You do the division first, you square it, you come out with 1.973, and that's what F is. Okay, you want to square the top number first and then divide it by the bottom number squared. Fine. Make sure you don't make a silly mistake. Me, I would divide first and then square. Okay. So the big issue now is to find the cutoff. You want, oops, got to put the marker down if you want to erase. So now we want to find the cutoff. And both ends happen to be the same. They both happen to be 40. We take away 1 and we get 39. So once again, I would love 39 on the top and 39 on the side. And I want that number right there. But no such luck. It doesn't exist. But that's really, really close to 40. 39 is close to 40. It's going to be relatively close to the 40-40 number. And if you look up 40-40, 40 in the left column and 40 on the top column, you would get the number 1.8752. 1.8752. Now, if you happen to go to 30-30 because you're afraid that maybe that's also the number, I put the box big because I need a lot of space to write down the number, but it's nonetheless it's by 30-30. That number is 2.0739. 2.0739. It is our exact answer is going to be in between. It's going to be in between. Okay, but it's getting to be a bit tricky here. Our cutoff, our F value, our F value is 1.973. 40-40 is 1.8752. That's the cutoff. Okay? Let me draw it bigger so people don't wonder why it looks like the center and not the right tail. Our F value from the test statistic is 1.973. In fact, I want to move that a little bit to the right. 1.973. Now, 40/40, which is close to 39/39, is to the left. It's 1.8752. And 40/40, which is far away from 39/39, is more than this number. It's 2.0739. I feel safe saying that the F value is to the right of our cutoff. Okay? And this is negative 1.8752. We accept in here, we accept HO. In this region here, where 1.973 is, we reject HO. Okay, so now what we need to do, and unfortunately I erased it, now what we need to do is write up our conclusion. In fact, we need to write down HO and H1 and whether or not we reject or fail to reject. Now we wanted to test that the two populations of quarters have the same standard deviation. So I hope I didn't write mu in the last problem, but it should be mu1 equals mu2. Just out of curiosity, I hope I didn't say that. Yeah, over here, over here and underneath. Everything in this box, it should not have said S1, it should have said sigma 1, sorry. It shouldn't have said S2, it should have said sigma 2. And in the center here, it should say sigma 1 equals sigma 2. Very sorry about that. It's a pretty big error. Okay. So, it says test the claim that the two populations have the same standard deviation. So the claim is that sigma 1 equals sigma 2. So since this is equal, the H1 will be not equal. You can never have equal with H1. All right. So now, since our F value from the test statistic, 19.73, is right here, it's to the right of 1.8752, we reject HO. But HO was the claim. The claim was HO. Okay, so we reject HO, and that means we reject the claim. There is sufficient evidence to reject the claim. There is not sufficient evidence to, so that means that we reject the claim, we reject this, that is, we support this. There is sufficient evidence to support the alternative hypothesis. There is sufficient evidence to support it. Okay, that finishes this section. Good luck with it.